Welcome to Full Momentum, an HEC-RAS podcast. I'm your host, Ben Cary. Welcome to episode 26, Chris. It's crazy. We're at episode number 26. We're going to be at episode 50 here before we blink pretty soon. So how are you doing?
I'm good, Ben. Good to see you. This is a crazy and exciting time of year. I know, especially for you. We got some fun stuff coming up. We're in the middle of a class right now that we're teaching. The weather's getting better. Yeah, it's a good time. And you're out in Hood River today, right?
I'm out in Hood River today. Yeah, we're
Cool.
teaching. We're in the middle of our online 1D 2D class, so there's a lot of RAS stuff going on right now. And there's also a lot of basketball going on right now. I know that's something, Chris, you and
Absolutely.
I both are really into. I know doesn't look like the Beavers are going to be in the big dance this year, but they've had a couple good runs in the past. So.
No, they won't be participating this year. We had a great run a couple years ago, which is a little out of the blue, and now we're kind of back to our usual mediocrity. So I'll be cheering on Gonzaga for sure. So how's Gonzaga looking this year? Or is this going to be the
Yeah,
year?
they're peaking at the right time, I would say, playing really well, better than they have all year. So that's good. They're not, because of some of the missteps early in the year, they're not going to have quite the seed that they have in the past. But it's the tournament. Anybody's got a chance, and it would be very Gonzaga to go the whole year or go the last 20 years without winning a national championship, getting all these one seeds, and then the year that they're a little bit down, maybe pulling off the win. That'd be pretty
Let's
cool.
hope for it. So what are they seeded this year? Or
Looking
will
like they're
be
probably
seeded?
going to be a three. They're probably going to be a 3 seed, but
Okay.
outside
That's
chance at
good.
2.
That's
So
still
yeah,
good.
yeah.
Who's the big competition out there? Who do you think has a
Oh
good shot at
man,
taking
yeah.
it?
So I don't want to make any of our RAS users upset of excluding their team from contenders, but Houston's got a very good team. Kansas, as always, remarkably, Kansas is very good. I know we have an employee at Kleinschmidt who did her undergrad at Kansas. So Cheyenne, I'm
Yep.
sure, is going to be rooting on the Jayhawks here in a couple weeks.
Yep.
A couple under the radar teams. Marquette, I really like Marquette this year. So if you're picking brackets and you don't watch a lot of basketball, they're kind of a fun upset team that could really do some damage. But it's the tournament. It's wide open. I spend a lot of time watching college basketball, and I inevitably always do very poorly in the bracket challenge.
That's the great thing about the bracket. It's the kind of thing where you don't have to be an expert to win it.
Yeah.
In fact, I've seen some people who don't know anything about NCAA basketball do very well in the bracket. And
Yeah.
so it's
Yeah.
anybody's game. Yeah.
Anybody's game, and we have a very, very exciting announcement tied to that. So this year we had the idea for the first time. Obviously, we've built over the last couple of years of doing these podcasts, and Chris, over the last number of years with the RAS Solution blog, we've built a very tight knit RAS community. We're starting to do these Pub&Grubs in different cities around the country, and we want to continue that growth and fostering of that collaboration and interaction with everybody who uses RAS in the US and around the world. And so for the first time this year, we are going to do what we're calling the RAS Madness Challenge, which is a traditional bracket challenge. So we're going to be sending out a link for anybody who wants to sign up. It's free, and you can fill out a bracket and compete against Chris and I and a number of other RAS users around the country. It's going to be a really cool opportunity if you haven't done a bracket before to learn how that works. And again, it's free, so no entry fee required or anything like that. If you're interested in signing up, in the description of this video, as well as the posting that is going out with the video, we will include the link to sign up. So it'll be through CBS Sports. You'll just need to create an account through CBS. It's free again to create that account, and then click on the link and you'll be able to fill out the bracket. Maybe even more exciting is the prizes that we have selected for the winners of the bracket challenge. So there'll be 3 prize winners, so first, second, and third, and each prize winner will get their pick of one of the prizes that we have. We haven't put together the second and third place prize, but the grand prize this year is going to be a free 1D 2D RAS class taught by Chris and I. And that can be either an online class for any of our online classes upcoming in the next year or two, or it can be free attendance to our in-person class, which we're going to be doing at the end of this summer. So, Chris, do you want to give a little bit of introduction to what that in-person class is going to look like?
Yeah, so we've got a class planned for Denver, Colorado, this August. The dates are August 1st, 2nd, and 3rd. And it's going to be our first in-person class that we've done since pre-COVID. So this is exciting. Yeah, get back together in person. This is going to be a 3-day intensive course. So it's all day, every day for 3 days, all about HEC-RAS. It's the same course we do online, but it's just going to be focused and condensed into the 3 days. And Ben and I will be there in person so we can walk around and help everybody with their workshops in person. And we got some exciting things planned alongside the class as well. So in addition to taking the class, you have an opportunity to join us for a pub and grub. So we're going to do a pub and grub in coordination with this class. Pub and Grub is tentatively scheduled for the 2nd, August 2nd. So that evening after the class, we'll all head over to a local pub and we'll have some local notable speakers who will have some presentations about HEC-RAS. And it's just a fun, casual, informal opportunity to hang out, learn a little bit about HEC-RAS, network around with some people, especially if you're a local Denver HEC-RAS user. You don't want to miss this because you'll be able to interact with other HEC-RAS users, experts in the field. And it's just a great time. Plus there's free beer. So, how can you beat that, right, Ben?
Exactly. Yeah. I mean, we had so much fun last year in Boise. And I know that this will be the 4th Pub and Grub. There were 2 that we did in Portland a number of years pre-COVID. And then we did Boise last year, and that was such a hit. So we want to really continue this momentum. I think our goal probably is to do at least one of these a year. And Denver was kind of at the top of our minds of a really good location that we haven't been to. There's a lot of really cool engineering, water resources engineering, and RAS modeling going on in Colorado and in that area. Obviously, you have Colorado State University as well as UC that are both nearby. So we're hoping we can really get a number of professionals, maybe some students and others that are just interested in the software together to learn through the class, obviously, and then also to socialize, network in that pub and grub. So again, just a reminder, the class dates are August 1st through 3rd. That's going to be a Tuesday through Thursday. And then the pub and grub will be Wednesday evening. So all of these, both the class as well as the pub and grub will be somewhere in the greater downtown Denver area. So if you're planning travel or thinking about if you can attend, that's kind of where we're thinking. We'll obviously let everyone know what the final locations are once those are set in stone. And we hope to have those by the end of this month. So stay tuned on more announcements for that. But we're super excited to start teaching in person again, because teaching online has a lot of great benefits, and I think we've really figured out a way to leverage that. But there's nothing quite like teaching in person. It's a really cool experience. And then to be able to pair that again with the pub and grub, which is kind of its own thing. Some people I feel like we would have people traveling just to go to the pub and grub. So to be able to pair that with some teaching opportunities, I think is really, really cool.
Yeah, so mark your calendars, August 1st through 3rd this year. Get your training budget all in order, so you're all ready to go as soon as the official announcement comes out. So stay tuned. We'll have that announcement out. You'll have a link that you can go to register, and then we'll see you there.
Yeah, and obviously with our online classes, we don't usually set a cap in terms of number of people that can attend. We might have a cap for the in-person class. So if you're interested, make sure you jump on that registration right away, or just go ahead and win the RAS Madness Challenge, and then you won't have to worry about registering because you'll have that free entry into that in-person class. And we'd love for you to join us in person. But again, if you enter the bracket challenge and you aren't able to or aren't interested in attending that in-person training, you're welcome to use that credit on any of our online classes, either this year or in 2024. So awesome. Anything else, Chris, before we move into today's technical topic?
I would just say, even if you aren't into basketball, NCAA, March Madness, maybe you know nothing about it, that's fine. Like I said before, beginners can do this bracket challenge. You can pick your teams by random. You can go with the higher seated team. A lot of people do that. It's really easy to fill this out. And if you are into it and you want to put some thought into it and maybe position yourself hopefully better to win this thing, you can do that as well. And I would also say when you sign up, you'll have a name, a username that associates with your bracket. Pick something that with your name in it, or something that we can tell who it is. That way it'll make it more fun so we can recognize people out there. But of course, if you want to stay anonymous, you can do that too.
Good. Looking forward to that. That's going to be very fun. Hopefully we have a big group of RAS users that are all competing in that. And then again, looking forward to seeing everybody in person in Denver, Colorado, August 1st, 2nd, and 3rd. All right, before we get into today's technical topic, which is going to be about kind of the differences between 1D, 2D, and 3D modeling, I just want to give a quick shout out to the sponsor for today's episode. Once again, our sponsor is Kleinschmidt Associates, the company that Chris and I work for. We're thankful to be sponsored by our firm Kleinschmidt Associates, who is known throughout the industry as a firm that provides practical solutions to complex problems affecting energy, water, and the environment. You can learn more at kleinschmidtgroup.com. So thank you, Kleinschmidt. And Chris, with that, I will turn it over to you to introduce today's technical topic.
Yeah, so Ben, today we're going to talk about 1D, 2D, and 3D modeling, the differences between them, when you would want to go from one to the other, pluses and minuses to both. Then we'll show some examples of different rivers or canals, and you and I will talk about, hey, what do you think? Is this a 1D, 2D, or 3D modeling application? So we'll have a discussion about that. I'm going to show some animations too, just to kind of show you some of the differences, and we'll see where this takes us. So first thing I want to do is bring up a document. I think this is a very important document. I've got a RAS model here opened up as well, but I want to bring over this document here first before we get into the software and introduce this if you haven't seen it. If you've seen it, just encourage you to read it again. But this is put out by HEC, the developers of HEC-RAS, and this is a companion document. So this is one that we should all have. Back in the day, I would say you should have it on your bookshelf or in your bookshelf. But nowadays, we all have them electronically. And you don't even have to save it on your computer. You can just go right to the HEC website. Here's the HEC website. I'm on the HEC-RAS page. If you go up to publications, you can find it in there. Just click on publications, and you can either browse through all of their publications. There's a lot of them, 42 pages worth. Or just remember this, TD41, TD-41, and that takes you right to model or application guidance for steady, unsteady, 1D, 2D, 3D modeling. So we're going to talk specifically about the 1D, 2D, 3D part of this, but this document does get into the differences between steady and unsteady. Maybe we'll save that for another podcast. I think that would be a good topic. Yeah. But give this a read through, have this available. This is something that would be very useful at the beginning of a project or even at the proposal stage where you're trying to decide, hey, is this application, is this project going to require a 1D, a 2D, or a 3D, or maybe some combination of all those. And so you can browse through this. I think maybe the most important part of this document is chapter 2, where it talks about the knowledge of the hydraulic system and the purpose of the hydraulic model. If you have a good understanding of the hydraulic system that you have to model and the purpose of your hydraulic model, what are the objectives? What are you trying to get out of it? What are the questions you're trying to answer for this particular project? That's going to help direct you into what modeling platform or what modeling type you want to use, 1D, 2D, or 3D. So it gets into the purpose of the model, knowledge of the river system, et cetera, et cetera.
Yeah, that's a really important concept that a lot of people kind of miss. And for some folks, 3D modeling is not going to be an option. That could be because of cost or licensing or inexperience using the software. And so it's not that you can't get information from a 2D model for a situation that probably would be better to use for a 3D model. It's more about understanding the limitations of what that model is going to be able to produce, what type of questions you're going to be able to answer with that model. Because again, HEC is going to be able to model just about every situation you could come up with. It's just a matter of what kind of answers you're going to be able to get out of that model, what kind of reliable information you're going to be able to extract from those modeling results. So I think chapter 2 is a great introduction to that. And we'll talk a little bit about some of those situations, I think, here today.
Yeah, and then it talks a little bit about data requirements, and then we've got steady versus unsteady here. And then chapter 6 gets into the differences between 1D and 2D modeling, and then chapter 7, 2D versus 3D modeling. And so definitely give that a read, but let's get into the differences. So I've got this model up. This is the Bald Eagle Creek data set. You all have, if you've downloaded the software, you can see I've got a slightly older version open right now, but that's okay. It's the same for 6.3.1, which is the latest version. But here you can see the Bald Eagle Creek data set. And the plan that I have open right now is the one called PMF with multiple 2D areas. This plan has the system set up as mostly a 1D model. So you can see here with these cross sections, and it's got some 2D areas off on the side. Now, what is a 1D model? What makes it a 1D model? Well, the first thing you'll notice is we have a lot of cross sections here. And in fact, in a 1D model, that's how you define the geometry of your system. The terrain is with cross sections. These cross sections are at discrete locations, and you either have them surveyed out in the field, or you can pull them right off of a terrain if you've got a good terrain map. Extract that terrain right onto the cross sections. And so every cross section has a look something like this. Here you can see a cross section with a main channel over here and a secondary channel over there. You can scroll through them upstream and downstream, but these are at discrete singular locations, and these are also called computation nodes. Now, what makes a 1D model distinctive is the fact that it is modeling in one dimension, and that one dimension is the downstream direction. So that doesn't mean you have to go in a straight line in one dimension. It just means that you have a singular direction of flow, and that's what you're modeling, that singular direction of flow, which can also be stated as the downstream direction, right? A 1D model does not account for flows that are not in that singular direction, that downstream direction. And in fact, the downstream direction is prescribed by you, the user. You're the one who determines the downstream direction. So here you can clearly see with this river center line that we have a downstream direction of flow, but you might imagine over here on the sides in the floodplain areas, you might have flow that's not necessarily going in the downstream direction.
Yeah, and you can capture some of that variety in flow direction based on what's called doglegging your cross sections. And you can see there's a number of instances in this model where that's occurred, where you want to draw those cross sections perpendicular to the direction of flow so that you're capturing that singular downstream direction. But if you have differences in terms of the direction of your flow in your main channel compared to your floodplain, you are able to capture that by doglegging your cross sections. The problem is twofold. One is if you don't know the direction of your flow, which can be the case if you have very, very wide floodplains and it's hard to tell what direction flow can go. And also if the direction of flow changes with the flow in the river system, which is also something that we see sometimes. And in that case, 1D modeling is going to be very challenging, and you're going to be better off using a different type of approach, such as 2D modeling.
Yeah, and this is a great example of that very thing you just mentioned, Ben, direction of flow. If we're modeling low flows through here, you might imagine that it's going to follow the Talweg of the channel pretty well.
Yeah.
So that's a very easily defined direction of flow. And you can see we've got our cross sections laid out perpendicular to our perception of the direction of flow. And that's why they're dog-legged here, because as flow gets out in the overbank, it's going to flow more straight downstream or down valley versus following the meanders of the channel. But here's the problem. What happens when you start introducing more flow and the water starts coming out of the river, out of the banks, starts spreading out unpredictably? if the water spreads out unpredictably, now you're starting to get into the 2D modeling realm, because a 1D model can't calculate direction of flow. Again, you prescribe it with how you lay out your cross sections. So let's say, for example, this water's flowing down here and you got enough flow that it starts to spill out and it goes this direction over here. Now, all of a sudden, we have a situation where water is flowing lateral to the cross-section layout. And the 1D model is not going to capture that. It's not going to capture that flow going lateral like that. The only way to do that would be with a 2D model. And so you could insert a 2D area right here in your model, an inline area, and let the 2D model sort out the direction of flow. So that's a big limitation with 1D modeling, is knowing the direction of flow is very important. Having high confidence that you know the direction of flow. Yeah, I was just going to say, there's a lot of situations where you just don't know the direction of flow.
Two other limitations, Chris, and feel free to correct me if I'm wrong on these, but two other main limitations of 1D modeling are the fact that you only get one computed water surface elevation per cross section, and you only get 3 velocities. You get a left overbank velocity, a channel velocity, and a right overbank velocity. And so you can imagine, especially for where Chris is looking right now, it's a pretty wide channel and floodplain. And the likelihood that you're going to end up with a single water surface elevation across that entire cross section and a simplification of only 3 velocities is pretty low. You're probably going to have a little bit more detail, particularly in larger flow events where you're going to have flow spreading out over that entire floodplain area.
Yeah. And even those 3 velocities are post-processed from a single average velocity on the cross-section. Now, the seasoned RAS users out there will know that there's a way in 1D RAS to get a velocity distribution over these sections, and you can do that. But that is simply based on a conveyance weighted distribution. So RAS will actually look at the conveyance in slices across a given cross section and then weight the distribution of velocities according to that. It's not a true 2-dimensional solution, but it can sometimes provide you some insight as to how velocity changes across the cross section. But again, that is just post-process. That's not actually computed. So it's not a true 2-dimensional solution. So you can see we've got some 2D areas over here. These are offline 2D areas that are added in. And kind of where we're at right now is it's very common to have models that have both 1D and 2D elements in them in RAS. And we do this a lot, Ben and I do, with our projects. It's very common to have both offline 2D areas like you see here, but also maybe inserting an inline 2D area as well in an area of interest, maybe say this part right here where we're not confident in the direction of flow.
Now,
so Ben, what are some of the benefits or advantages of 2D modeling that you have over 1D?
Yeah, before we get into that, Chris, I do want to just stick up for 1D modeling a little bit, because we just spent a few minutes talking about all the things that it can't do. But for those who haven't done a lot of 1D or 2D modeling, what are the reasons that people even use 1D modeling? Because I think based off, if somebody had never done any modeling and they just listened to us talk for the last 5 minutes, they'd say, well, why would I ever use 1D modeling then?
It's a very common question. Yeah. So
what would you say the answer to that question is?
The number one answer by far is computer runtime. And I would say maybe a number 2 would be modeler familiarity. Maybe you've come up doing 1D models. You're very comfortable with it. You know how to set it up. And maybe a third thing would be data availability. Maybe you don't have a terrain. Now, these days, that's pretty rare. You can usually find terrain and decent terrain just about anywhere. But let's say you don't, but you have some surveyed cross sections. Okay. Well, then you may want to go to a 1D model. But by far, it's runtime. Runtime is the big thing, because 1D models have a lot less computation nodes. You can even see in just this view I'm looking at right here, this stretch of river through here has maybe 50 cross sections, 60 cross sections through here, 60 computation nodes. You go and look at the 2D area over here, and we've got hundreds, if not thousands, of cells, each with their own cell center and several faces around the cell. So those are all computation nodes. And so the run times are just much, much longer for a 2D model. If we were to make this all 2D, you'd probably see this model take maybe an order of magnitude longer. By that, I mean the cross sections may take a minute A really complex 2D model could take up to an hour or even longer. I mean, we've had some models, Ben, that have even run overnight sometimes, for several hours, up to maybe even half a day at sometimes. And we try to avoid that. And one way to avoid that is to put cross sections, put 1D reaches where you don't need to have that kind of information. You don't need the detail. You're confident in the direction of flow. You don't care about hydraulic parameters lateral to the primary direction of flow. You know, those can all be set up as 1D reaches, and your model's going to run much faster.
Yeah. Yeah, it's interesting because your point about data limitation used to be maybe the primary reason why 1D modeling was used, because, it wasn't too long ago where it was difficult to find quality terrain data that could be used for 2D modeling. Nowadays, that data is so readily available for almost anywhere within the US. And even if you don't have a data that is of quality to be used in a 2D model, it's fairly affordable to get that information now as well. So that really isn't a limitation for 2D modeling anymore, and not necessarily an advantage for 1D. So yeah, it's really runtime. And then the only other thing that popped into my head, Chris, is still around the idea of the models that are required to do FEMA mapping, right? Encroachment analysis and floodway analysis. The standard is still to do 1D to do that sort of analysis. There's some really cool groundbreaking work going on through FEMA, through HEC, on developing standardized approaches for doing that in 2D, and that's going to be here sooner than we think. And that's going to be a huge development, but that's another reason why folks might use 1D modeling at this point. And another reason why it's important to still understand what goes into 1D model and what the limitations and benefits are of that. But your question that led into that was, what are the advantages of 2D modeling? And needless to say, the advantages of 2D modeling are kind of opposite of the disadvantages of 1D, and that is you can have multiple water surface elevations within your 2D mesh. You can have the direction of flow computed by the software, not determined by the user. You can get variations in velocity. You can get a lot of intricate flow detail that you're not able to get with 1D modeling. And again, that's because in our 2D mesh, we're not defining the direction of flow by drawing cross sections. We're allowing the computational engine of HEC-RAS to use the underlying terrain data and our cells within our 2D mesh, both the cell size, this orientation, to determine what the direction of flow is, what the velocities are, what the depths are, and what the water surface elevations are. What else stands out to you, Chris, in terms of the high level advantages of 2D modeling?
Yeah, I mean, to me, that's the biggest thing is direction of flow. RAS can figure that out in a 2D area. Here you can see a 2D offline area is part of this complete 1D 2D model, but you can set up a model that's completely two-dimensional, no 1D elements at all. That's no problem in RAS, and that's a very common thing to do. In this case, we're looking at an offline 2D area that's connected up to the 1D. Now, why is this a 2D area? Well, when water gets high enough in this river to spill over this road that you see here, kind of delineated with the red and black line, when it gets high enough, it's going to spill in here and it's going to move around this area unpredictably. We don't really know how water is going to move, the direction of flow, and how fast it will get from one place to another in this area. So it's set up as a 2D area. You can see all the individual cells with their cell centers in there. And with this setup, RAS is able to figure out the direction of flow and have a really nice distribution of velocity all throughout. And one of the cool things about 2D modeling too is once you've run it, you can turn on the particle tracing and you can see these flow patterns that HEC-RAS calculates in the 2D area. Now you can do particle tracing with 1D as well, but that particle tracing is based on the concept of everything is moving in the downstream direction. So it doesn't look quite as realistic and as complex as what you'll get in a 2D area like this.
Yeah, some really cool animations, really cool results that you can get with 2D models. And there's also been some pretty big developments in terms of limiting the limitations of 2D modeling with newer versions. A couple things that come to mind right away would be, previously up until about a year and a half ago, you're not able to do bridges within 2D, and that was a big limitation for the software, but that was remedied by the addition of being able to do bridges in 2D with the version 6.0 release. So now we can include bridges in our 2D area. Computational runtime wise too, like Chris mentioned, 1D models are certainly still a lot faster than 2D models, but we have a lot of more tools at our disposal to allow us to run very large, complicated 2D models. Cloud computing is something that Kleinschmidt uses to really allow us to run large models quickly, or as quickly as we can. And that's something that, just like the availability of terrain data has become so much easier to get to, the availability of cloud computing resources to use souped up computers to run our models faster are also more available and becoming more widely used around the industry. So even though there are still some limitations with 2D modeling, those limitations are becoming less and less significant. And so because of that, it's not surprising that you're seeing more and more 2D modeling being done because of the level of detail that you can get with that sort of simulation.
Yeah, exactly. And one of the cool things too about this data set that I've got up here, and again, this is the one that comes with the software, it's the Bald Eagle Creek, is you can look through the different plans and you can see different ways to set up. And this gets to the discussion we had earlier about knowing the objectives or the purpose of the model. What are you trying to get out of it? And if it's an overall planning study, maybe you get away with just doing cross sections and have a really nice, fast moving model, but understanding you've got some limitations, especially when flow is going lateral to the downstream direction. But here you can see we've got a 2D to 2D run. And if I open this one up, you'll see in the geometry that this is a completely 2D model. There's no 1D elements at all. In fact, it's two separate 2D areas, one upstream of the dam in the reservoir and one downstream in the routing reach. So this is a completely two-dimensional model. And one of the common misunderstandings out there is that 2D modeling is more difficult than 1D modeling. And actually, you can make an argument that a 2D model setup is much easier, because look at what we have here. We've got a system where we've got flow moving down here. All we have to do is draw the perimeter of our 2D areas, put in a mesh, put some boundary conditions on it, and you're ready to go. Now, it's not going to be a complete model because you have to do some improvements to the mesh where you might need some break lines or some refinement regions, things like that. But just to get it up and running, it's really easy to do. If you remember the image I had here of the 1D model, you had all these different cross sections. You would have to go through for each cross section, determine the bank stations. You need to determine the reach lengths, the terrain that goes on the cross sections. You would also need to put on ineffective flow areas. And this is one thing we haven't mentioned yet, but this is a huge advantage in 2D modeling over 1D. In 1D, whenever you have areas of your cross section where you've got flow that's not actively moving in the downstream direction, it could be ponded water, or it could be actually going in the upstream direction or lateral to the main flow path. Those have to be defined as ineffective flow areas. And it's a very subjective exercise, a very time-consuming exercise, and can be very difficult to get those set up properly. In a 2D model, you don't have to worry about ineffective flow areas. That is all part of the computations. And so RAS will figure out those ineffective flow areas for you. So that is a huge advantage. Yeah.
With one caveat, Chris, and that is kind of gets into my next point, which is, yes, I agree with you 100% that, 2D models are actually easier to set up and take a lot less time to set up than 1D models. But there are a lot of computational choices in 2D modeling that are very difficult to understand if you haven't had formal training or experience working with them. It's also very difficult I think it's a lot more difficult to troubleshoot and pick out instabilities or errors within a 2D model compared to a 1D model. If you've done a lot of 1D modeling, you know that looking at your profile line and your cross-section outputs are great ways to diagnose, oh, look, there's a really funky thing going on with my water surface elevation at this location. There must be an error or instability at that point. With 2D, it's a little bit more detailed, a little bit more difficult to grasp what to look for and what are indications of instability or errors, because 2D modeling is in some ways a lot more stable than 1D modeling. And so it can handle a lot of instability and errors that with a 1D model, it would crash the model and you get that red line of death that we're all used to as hydraulic modelers. But with 2D, you can kind of power through a lot of bad computations, a lot of errors within a model, and you can end up with a result that says it ran to completion. It didn't have any reported significant errors that cause the model to crash. And so there's a nuance in understanding how to work with the results of a 2D model. And back to your ineffective point, it does compute those ineffective areas, but really only effectively if you have the full momentum set of equations turned on. If you're using diffusion wave, you're really not going to be picking up what those ineffective areas are. And so again, that kind of gets into the weeds a little bit about why it's really important to have either some formal training on 2D modeling or have a lot of experience using it and know what to look for and which computational options to select, because there's a lot more nuance with 2D modeling than 1D.
100% agree with you. Yeah, and don't get me wrong, it is easy to set up, but that doesn't mean you've got a good model.
Yeah.
But if you want to just get something up and running, you want to take a quick look at, hey, what are we looking at here? You can get a 2D model up and running literally in minutes if you already have a terrain developed. But yeah, that doesn't mean it's a correct model. That doesn't mean it's accurate. But it is up and running. So the next step then is refining your model, and you do that in both 1D and 2D. But you brought up a great point, Ben, which is the stability aspect. Those of you who've done unsteady 1D modeling for a long time will know exactly what I'm talking about. But 1D models, unsteady models, can go unstable very easily. In fact, I expect my 1D model usually to go unstable the first time I run it. And then you have to go in and you have to fix it up. 2D models are much more robust, as you mentioned. In fact, if you have your correct, if they fall within the guidelines specified in the manual, you're likely to have a very stable 2D area. Doesn't mean it's right, but it means it's stable and you don't have to worry about your model crashing. Now, it still can crash, and there are some things besides Courant numbers that can cause your 2D area to crash, but there's a lot less things that will cause it to crash than, say, in a 1D model. Mm-hmm. So what are some limitations to 2D modeling?
Yeah, we've touched on a lot of them already.
Great, right?
Yeah, exactly. So obviously computational runtime is probably the biggest one, particularly for larger areas. The understanding of how to troubleshoot and diagnose 2D modeling is something that takes formal training or takes a lot of experience. If you're interested in learning more about working with 2D models and using a combined 1D, 2D models, Chris and I teach 1D, 2D modeling classes both online and in person now as well. So definitely keep an eye out for the next class if you're interested in learning more details about 2D modeling. But those are the two limitations that stand out to me, Chris, right away. There are also some limitations, and this gets into our next modeling topic when it comes to three-dimensional flow. So you want to talk a little bit, Chris, about, because up until this point is interesting. If we have anybody who's listening to this episode who's followed us for a number of years, we did an episode back in episode 10 that was all about 1D or 2D modeling. And I think we called it 2D or not 2D. And so up until this point, the podcast is probably very similar in terms of the discussions that we've touched on, but we wanted to add a third modeling point, and that's just based on our experience about where the industry is going, and that is the more and more prevalent use of 3D modeling. And so, Chris, you want to touch on some of the limitations for the 2D models that maybe would cause somebody to look elsewhere in terms of a different computational engine?
Yeah, so the biggest one with 2D models is you get a single velocity per cell face, a depth average velocity. So 2D models do not account for vertical accelerations or vertical variation in velocity or other hydraulic parameters. And so if that's of interest to you, if you're trying to model something where vertical accelerations are prevalent, that is a key indicator that you want to start thinking about a 3D model. I'm going to bring over this example here. This is a project that we worked on here at Kleinschmidt. It's a nature-like fishway. So it's a way to simulate, it's a way to provide a head drop at a dam that's a more natural condition. So instead of having just a weir or spillway, we've spread out the head drop over several individual drops made up of boulders or simulated boulders. In each boulder, there's a gap in between them, and fish can swim up in between the gaps. They can hang out and rest for a while before they go up to the next gap. So this is something a fish could swim through quite easily versus trying to go over a spillway. But here you can see we've modeled this with a 2D model using the full momentum equation. So you can see the flow patterns in here. I animate this, you can see the eddy patterns and the shadow effect behind these individual boulders. You can see how flow bends around to find different flow paths through the gaps. But keep in mind, while this looks very realistic from a bird's eye view, everywhere in this model where you pull out velocity, that's going to be a depth average velocity. You can imagine as water spills through these gaps, you've got quite a bit of vertical acceleration going on. In addition to horizontal acceleration, but you've got some vertical acceleration, and the vertical acceleration is not picked up in a 2D model. So here's an example where we've got a 2D model here. It does a good job showing flow patterns, probably a good job showing head drop over these individual boulder weirs that you have here, and maybe a good idea of what the fish would experience in between here. But if you're talking about structural stability on these individual boulders, you probably need to have that third dimension, that vertical dimension, to have an idea of your distribution of velocity in the water column going from the surface down to the bed. And so that's not something you'll get in a 2D model, but you can certainly get that in a 3D model. And so that might be an indication that, hey, we're ready to go. Now, the same thing with 1D to 2D, going from 2D to 3D, you're going to have even longer run times. 3D models take a very long time to run. There is a bit of a high barrier to entry for a 3D model. There's a big learning curve. There are some different applications out there that are easier to use than others. Some offer some
cheaper,
and some are cheaper than others. Some offer great technical support. Some of them you're kind of on your own. So one model software that we use for 3D modeling is Flow 3D. We also use Star CCD or Star CC3.
CCM, I think.
CCM. Okay. Yeah. Sorry. I haven't used that one, but I know that we have some modelers in the company use it, but we mostly use Flow 3D. And Flow 3D is quite expensive, but it is a very, very powerful program. And it can not only do hydrodynamics, it does fluid dynamics, meaning it solves for any kind of fluid, including air. And you can even have models that have air-water exchange. So let me bring up an example of that. This is a model that we built to simulate flow going through a gate here. This is a dam, reservoir on this side. It goes through a gate into a tunnel, outlet works. Then we've got a kind of a barrier or energy dissipation weir right here, which shoots the water straight up into the air to burn a lot of energy. And one of the objectives of this was to model, do we have enough air entrainment coming from this air supply pipe to keep this relatively stable in here? It's one thing you don't want is you don't want a lot of pressure fluctuations at the gate that can damage a gate. And you want to have a relatively smooth flow in here, make sure you have enough capacity. So this actually looked at the air-water exchange inside here and the air entrainment that you would get from this air supply pipe. But also, look at this right here, this water shooting straight up. That's a great example of vertical acceleration, right? You got water that's moving downstream and then all of a sudden it shoots straight up. You're not going to get that with a 2D model at all. And you look at the complexity and the detail that you can get with a 3D model down here. It's pretty impressive. But again, there's a pretty steep learning curve for 3D models. There are some free 3D models out there. So if you want to put the time and effort into it, you can learn how to use some of the free software out there, open source software like OpenFoam or Delft 3D. Those are two examples of free open source software. But to use that, you have to be somewhat of a programmer. You have to know how to write code and how to compile code and get into a coding environment. It requires you to it's not just a graphical interface. So you go in and enter your data and press go. you've got to get into the code and manipulate that. And you have to compile your project and run it that way. So it's a little bit more difficult. I see a lot of academics using OpenFOAM because they've got the time and they've got the resources to learn how to work in a coding environment to run that. But for consultants, people who are doing work, project work, Flow3D seems to be a good alternative to that, but it is expensive.
Yeah, Flow3D is a great software, and there's they've done a really good job marketing that software. So there's some great videos online you can find either on YouTube or on LinkedIn. Brian Fox is an employee of Flow3D, and he's a great follow on LinkedIn. He shares a lot of cool stuff. So if you're interested in learning more about Flow3D, there's some great resources out there. And again, Clenchment uses it quite a bit. It's a very cool software that allows us to look at some of those situations that our 2D models can't handle. Similarly to, Chris noted the computational limitations of 3D modeling compared to 2D modeling. And so there are situations that, much like how you might model a larger river system with 1D cross sections, and then a smaller area of interest with a 2D model, we do the same thing with 3D models, where we might do 2D modeling of a reservoir and the downstream reach, and then we might build a 3D model to represent the spillway or some of the complicated hydraulic features of a dam or another hydraulic structure. And so you can kind of piece together different modeling softwares to solve the types of questions that you want to answer for any particular area of that study area. So yeah, some pretty cool tools out there that are available for us. And again, it's important to understand what you're trying to answer with your model, what type of questions you're trying to answer, figure out the information that model can provide you, and maybe more importantly, what it's not going to be able to provide you, and then choose the software and the setup that's going to be able to best and most quickly answer those questions for you.
Yeah, and 3D models are typically going to be limited to very small footprint areas, discrete locations, or individual structures, maybe a bridge pier if you want to model the forces on the bridge pier, the flow patterns around that, or spillway, for example. You'll model that in 3D, which actually brings me to another limitation we forgot about, Ben. In 1D and 2D modeling, specifically HEC-RAS, there is that kind of maximum slope recommendation. So if you look through the manual, you'll see that RAS talks about the computations tend to break down when you get about to a 10% slope, 1/10 slope. That's where the equations used in HEC-RAS don't really work so well, both 1D and 2D. So if you do have an application where you're looking at flow on a steeper than 10% slope, that's another indication. Maybe you want to look at a 3D model. 3D models can handle that. Plus, when you get to those kinds of structures that are really steep like that, you've got a lot of vertical acceleration, especially right where flow enters into that structure and where it leaves that structure. A lot of vertical acceleration going on.
Yeah.
All right. So, Ben, I want to quiz you a little bit.
Okay.
Let's talk about some different examples here. And you can tell me what you think if it's a 1D, 2D, or 3D modeling application. Now, obviously, we talked early on about the knowledge of the purpose of the model and the system you're running are very important. Here we can get a little bit of an idea of the system that we're modeling. We don't necessarily know the purpose of the model study. So we have to take some liberty there. But in looking at these, tell me, what do you think? 1D, 2D, or 3D model?
Yeah, so the thing that pops right in my mind first is that obviously you have a very sinuous channel, which, at first looking at it, it's like, okay, that's kind of complicated in terms of the direction of flow. Maybe that's 2D, but at the same time, it's very single thread channel. There's not much of a floodplain. The direction of flow is going to be very predictable. I'm going to assume that little notch at the tail end of the horseshoe is not that tall, so you're probably not going to have overtopping during high flow, which might change my answer. But assuming that that's tall enough where you're not having overtopping, I would say that this is a very reasonable area to model with 1D cross sections. Again, with the caveat, of the purpose of the model, because if we were proposing to put a bridge over this river and compute bridge scour around an individual pier, you might end up actually wanting to model that particular segment of your model in 3D. But 1D is what stands out to me. Chris, do you agree?
Yeah, I agree. I mean, you could see you could easily lay out cross sections right here.
Yeah.
And especially at this flow condition, this is very, very one-dimensional. Now, when you go around a bend, really anywhere in a river, you have three-dimensional processes going on. But especially at a bend, you get this helical flow going around, and that's a very three-dimensional process. So you're not going to capture that, but that's a lot of times not important. The other thing you're not going to capture with a 1D model is super elevation of flow. As it goes around this bend, you actually have water that pushes to the outside of the bend a little bit, and it super elevates the water surface. You're not going to get that with a 1D model. You can get that with a 2D model. So that if that's important, that might be an objective or purpose of your model that would lead you to a 2D application. Of course, make sure. Yeah, go ahead.
That's a really important one, Chris, because we always, we harp on do you know the direction of flow? If the answer is yes, 1D is probably okay. But one important caveat there is, well, even if you know the direction of flow, do you have some of these other hydraulic effects, such as super elevation, which you're not going to be able to capture with 1D models? And we've actually had that situation where we've modeled something in 1D, and we've done some design with those results, and then realized, like, oh crud, there's some super elevation because of the velocities here. We need to actually transition to 2D so that we can capture what the differences in water surface elevation are on the inside of the bend to the outside of the bend.
Mm-hmm. Yeah, and in this example, maybe super elevation is not a big deal because the channel is very confined, and it's very high wall. It's a deep canyon here, so there's probably not a lot of adverse implications if you get the water surface a little bit wrong at the outside of the bend here. But imagine a case where you don't have these high canyon walls and you've got a levee over here, and your 1D model is showing you that you're just below the levee, but that's not accounting for super elevation, where maybe that super elevation pushes it above the levee elevation. So that would be an important thing to consider.
Good.
All right, let's go to the next one here. What do you think about this, Ben?
So we got a cascade channel, looks single thread, not a whole lot of access to the floodplain, heavy vegetation in the riparian areas. So again, this one to me, actually, I would say is very reasonable to model with 1D. If you're very interested in getting some more detailed flow patterns, perhaps you're doing a fish passage analysis, then that might push you towards doing some 2D analysis in this area. And again, if you're trying to get velocity distribution vertically within the water column, you're not going to be able to get that from 1D or 2D modeling, so that might push you to 3D. But just based on the looks of this, I would say very reasonable to model this with 1D.
Yeah, I think you're absolutely right. I mean, again, like all of these, there's going to be a discussion about the objective of the model. That's going to play a big part in this. But if you're just doing a reach-wide study here, you can put some cross sections across here and have a really good approximation of head loss through here and the overall water surface profile. But like you say, if you're interested in fish passage conditions through this, you're going to need something more detailed than a 1D model, maybe even more than a 2D model if vertical acceleration is prevalent through here, which it looks to me like it is. Anytime you see white water, that's a good indication you've got vertical accelerations happening. So boils down to the objective. First glance, you might think 1D, but it really depends on the objective of the study.
Yeah, the one other caveat with that particular reach there that's often not considered is how difficult is it going to be to get quality bathymetry data in that reach? I would say pretty difficult. So that's another thing that might push us in one direction or the other is, whenever you have that much white water, that much turbulence, that much air entrainment within the water column, it's going to be difficult to get bathymetry data, both from a safety standpoint, if you're going to do a hand survey, and also from a green LiDAR standpoint. And so that also sometimes is a limitation where it's like, hey, we would love to model this in 3D or 2D, but we just have no idea what the bathymetry is. So we're not going to, make up data with the 2D model. We're going to go ahead and just approximate the bottom of the channel and then model this with 1D.
Yeah. It'd be fun to kayak that though, huh?
It would be. I agree.
Okay. Apologies for the poor image quality here, but what do you think about this?
Well, Chris, I'm going to have you add one piece of information so that I can make a better decision. What's the purpose of this model?
The purpose of this model is to assess the flood risk at some property right over here.
Got it. So in that case, obviously you have a channel that's spread out between two, looks like large mountain canyon walls. Definitely have some side channels, some oxbows, and some interconnected channels that probably change the direction of flow pretty significantly depending on what the flow is. And if we're talking about flood risk, we're probably talking about high flows within the system. And so in that case, I would say probably going to need to do two-dimensional modeling for this particular scenario. You might be able to get away with 1D a 1D portion of the model upstream and downstream of our particular property of interest, and then an or inline 2D area within our area of interest. But it looks pretty two-dimensional to me. You concur with that, Chris?
I do. I agree. Back in the day, before we had 2D available in HEC-RAS, we would try to shoehorn a 1D model in here and make it work, and doglegging your cross sections, maybe putting a lateral structure here with an off-channel storage area over here, but it's not going to be very accurate, very precise. What would be great is just to draw a big 2D area around this and let RAS sort out the direction of flow, and you could do that for all different flow levels as well. So,
the interesting thing about that too, though, is again, if you were assessing flood risk at a property there on the left overbank, and you were doing this for a dam breach analysis, I might actually argue that 1D modeling would be better, because the flow level is going to be so large that you're probably not going to have different direction of flows within this canyon area. It's probably going to just be a large wave of water moving in a single direction. So that's why the flow level that you're modeling is so important to understand before picking the software type.
Yeah, you could just completely inundate this entire area and water's just barreling straight down through here. Yeah, good point. Another bad image, but I think you can see what we're dealing with here. We've got a main stem right here and a tributary coming into it and a junction location. A lot of property right here, a lot of infrastructure, potential consequences there. So again, I'll throw out a objective. The objective of this study is to evaluate the potential consequences of flooding right here. And let's just say a dam break.
Yeah, so this one, again, dam breach analysis. So you're thinking right away, really high flows, probably not going to activate a bunch of channels, not going to have differing directions of flow. But this is a junction. And anytime you have junctions, that's going to be pretty difficult to capture the complexities of the hydraulics at that junction, particularly for a dam breach analysis where those forces can be pretty significant. And so I would say you would probably want to do a 1D model for the majority of the reach leading up to this, but then at the junction and around the junction, probably have an inline 2D area to capture the complex hydraulics that occur at this location.
So you guys out there listening to this are probably thinking that I prepped Ben ahead of time because he's nailing these. And so I just want to let you know that Ben, this is the first time Ben is seeing these images. So I'm very impressed, Ben. You nailed it. This junction here, this is the problem. Junctions are very difficult to model in 1D. 2D, they're very easy. You just, like you say, put an inline 2D area around the junction. You could have some 1D reaches coming in and going out, but let the 2D area sort out the direction of flow. And especially when you talk about going from low flow to high flow, the direction of flow and the interaction at this junction can change dramatically at different flow levels. And that can be picked up in a 2D model, but not a 1D.
And Chris, if we go back to that, not to throw this question on you without any heads up, but what's the real challenge of modeling junctions with 1D? Why is that such a problem?
So you've got flow moving in different directions as it comes together. So number one, laying out cross sections is very difficult. Okay. Then to compute the energy loss over that junction, you have two options in RAS for 1D. You can compute it as energy, or you can use the momentum equation. Neither of them really handle the energy loss through that junction very well. And in fact, junctions in 1D, especially an unsteady flow model, are notorious for being areas of instability or where you get a lot of errors thrown out, especially in steeper rivers. Now, this may not be that steep of a river, but if you had a really steep, say, mountain river tributary coming into another steep main stem, try to put a 1D junction there, that can be very difficult to model. So yeah, 2D area is much easier and more accurate. All right, what about this one?
Yeah, so that's very two-dimensional, wide floodplain, multi-threaded channel. Good luck drawing enough dog legs to capture all
Exactly.
of the direction. I know you've done something like that, Chris, because you go if you're at a high enough elevation, this could be the pathway of the Missoula floods, and I know that you did that one time with a 1D model, and I know how challenging that was to set up. So you, in theory, could do this in 1D, but you're going to save yourself a lot of time building this as a 2D model, as long as you have good terrain data, which is a big limitation. Because if this is in a remote part of Alaska, you might not be able to capture lidar for this entire area. You might have to just approximate it with cross sections. But if you have good data, clearly a better 2D modeling application.
I agree completely. It's so much easier to do this as a 2D area. If you were to try and do this in 1D, there's two ways you could do it. One, you could just draw cross sections all the way across the floodplain, and you'll have multiple threads of this braided channel in a given cross section that show up. Now, this gets to our limitation with 1D, and that is you get one water surface calculated for each cross section. And so if you had a cross section that spanned this entire thing, all these different threads would have to have the same water surface calculated. Well, that's not going to be very accurate. The other way to model this is to split it up into multiple parallel reaches, all kind of combining at little junction points. So like this could be a reach right here with the little some little cross sections on it. This could be a reach here, put a junction here, and then it continues on down here. And then you've got these other parallel reaches, and you try to tie that all together. That's a complete nightmare to try and set up in 1D. I've tried it before. I've done it before. It's not easy, especially for a long reach. Now, if I see something like this, it's going to be a 2D model every single day.
Yep.
And the great thing about RAS 2D modeling is RAS will figure out the direction of flow for you. It'll figure out the distribution of flow in each of these different threads. You'll get different water surface elevations for each of these different threads, which can be extremely important. All right, how about this one?
Yeah, it's another one that probably is going to be two-dimensional, just simply because of how low those connection points are between the different horseshoe bends. The direction of flow is going to change pretty significantly depending on the flow level. So this one to me is a 2D model.
What if I told you the objective of this was to model low flows just to assess, water quality, for example, during low flow conditions?
Then yeah, 1D modeling is probably very reasonable in that case. But again, 2D model might be just easier to set up. So
yeah, exactly. It's going to be tricky to dogleg cross sections through here, but if you're modeling this condition only, you could do it with 1D cross sections probably pretty easily. But yeah, as soon as the water gets up and it goes over these saddle areas on the bends, then it's very tricky, especially if you're going from low flow to high flow in a single model. All right, how about this one, Ben?
That one's pretty clearly one-dimensional.
Yeah.
Maybe if you have some high flow spilling out of that area, you might have some two-dimensional flow in the floodplain. So that could actually be an inline or an offline 2D model where you have a 1D in the channel and then 2D in your offline areas.
Yep. Yeah, but if the water's staying in the canal, this is about as one-dimensional as you can get. That being said, doesn't mean you can't do a 2D model. Maybe you don't have cross sections yet, but you've got good terrain of this canal. You could easily do a 2D model through here. Just make sure you get enough cells going across the channel, 5 to 7 at a minimum, and may even be easier to set up that way. But yeah, this is very one-dimensional, so cross section would be perfectly fine here. All right, what about this one?
Oh, interesting. That's the same image I just found. I was pulling it up. That's hilarious. Yeah, so you got to give me a purpose, Chris. This one's pretty important to have a purpose on.
Okay, so the purpose here, there's two purposes. One is to make sure our wall heights are high enough to contain the design flood, and the other is to determine the structural stability of these baffle blocks, these energy dissipation blocks at the downstream end of this spillway chute.
Gotcha. Yeah. So obviously we have a lot of vertical acceleration of flow when you have a spillway this size. You also are going to have some variation in the velocity in the water column, particularly at the end of that spillway where you're having water shoot up. A lot of complexity here that's just going to be impossible to capture with a 1D or a 2D model. So based on the purposes you described, clearly this is going to need to be a 3D model for us to have some reliable answers to those questions. If the purpose changed and you were more focusing on just routing a flood across the spillway, you could probably represent, the spillway with an SA2D area connection in a 2D model, or with an inline structure or a dam in a 1D model, but you wouldn't be able to have any of the answers to the questions that you proposed, inside of that structure itself.
Yeah, what if somebody said, hey, we're at a 5% design right now. We just need to get some ballpark ideas about what we're dealing with here. 5%, we're not holding you to this, could you model this as 1D?
Yeah, you could. And the water surface elevations might not be all that different in the spillway itself. At the downstream end, you'd probably end up with pretty significantly different answers, but you could get some approximate answers, and that might be a good starting point, as long as you and the client understand what the limitations are of those answers.
Yeah, we've done this before too. In early stages of a project, we want to get just a quick ballpark idea of what we're dealing with here. Just throw some cross sections on there and run it. Now, the thing about something this steep like this, you would need very closely spaced cross sections. Or if you're doing this as a 2D model, you need very small cells on here to get a decent answer. But yeah, you could do it, but for the objectives I laid out at the beginning, you would definitely need a 3D model in this case. This is the Dalles Dam, kind of close to where you're at right now, Ben, just a little upstream on the Columbia River from Hood River. And you can see the reservoir right here. It's kind of an odd shaped dam. It's got this L shape, backwards L shape to it. You've got the spillway over here. You've got a navigation lock here. You've got the powerhouse over here, a non-overflow section, embankment section here. Let's say we are modeling, this is a very kind of a Columbia River reach wide model study where we want to assess, what kind of water levels are we getting throughout the system for a probable maximum flood.
Yeah, so in that case, obviously the Columbia River is pretty large, so this is probably going to be modeled with a 1D river reach, and the structure modeled as an inline structure or a dam in the case of a 1D model. The challenge with that, obviously, is you have that portion of the dam that's parallel to the direction of flow, and so really to get any accuracy in that tail race area, you're going to have that as a 2D model. But based on your description, you would just kind of chalk that up and say, hey, we're not going to have great results in that area of the model, but it's not our objective to get an understanding of what those flows or what those water surface elevations are. So
yeah, I think for a reach wide 1D model, you could put a cross section right here, and you could put another one here.
Yeah.
And then somehow kind of figure out what the head loss is through this dam structure itself. Or if you wanted a little bit more complexity, you wanted a little bit more detail in here, maybe some understanding of flow distribution going over the spillway versus the powerhouse, you could still do a 1D model and have a reach coming down here like this, with cross sections that terminate at the dam. They go across from the north shore to the dam, and then you could have a secondary tributary reach right here with some cross sections in here. Make this a lateral structure, make this an inline structure, have a junction down here where this side channel comes together with the main channel, and then continue on. That would be a little bit more complexity if you need it in this area. But again, this might be something, if you need that kind of detail, it might be easier just to do a 2D model and have a SA2D connection here to represent the dam, and let RAS sort out the direction of flow through here. Yeah. All right, so this next one is a nature-like fishway. I showed you a video of a simulation, a 2D model simulation of something like this. You can see these array of boulders that create these different weirs and drops to kind of spread out the head loss over some distance so that fish can actually swim up through this. So the objective here would be twofold. One would be to figure out what is the overall energy loss of this structure, what's the resulting water level upstream for a given flow rate, but also the other objective that we'd like to get some answers for are, what are the conditions in here? Are we meeting fish passage criteria? Are each of these drops below a certain threshold that's been provided to us? Are the velocities slow enough through each of these notches?
Yeah. So I'm going to kind of answer this in a different way, Chris. I'm going to say you actually are going to need both 1D and 2D models here. You're going to need the 2D model to understand some of the hydraulics in between the boulders, in between those drops, get a better understanding of what the velocity patterns are. But as you can see, assuming this river is within a FEMA regulatory boundary, which based on the size of the river, it probably is. This is work that's being conducted inside of a floodway, and so my regulatory hat is on and saying that you're going to need to perform some sort of no-rise analysis or a CLOMAR related to this, and so you're probably going to need to build a 1D model to be able to answer those questions as well. So we've actually had a couple of projects just like this, and we've built a 2D model to answer some of those more fish passage related questions, and then we've done the 1D model for the permitting and regulatory side of things. So
again, you nailed it, Ben. That's exactly what I was thinking. You could even argue that we would need a 3D model to go with this.
Perhaps.
If you're worried about stability of these boulders and you want to have a really good idea of the forces on the individual boulders. A lot of times, though, we over-design these boulders so they're strong enough by a huge factor of safety to handle any flood situation we might have through here. And so maybe you can bypass the 3D model in that case. But yeah, definitely 1D and 2D to address those objectives that I talked about at the beginning. All right, here's the last one, Ben. This is a fish ladder, kind of a unique style of fish ladder. In fact, I'd never seen one like this before I went looking for a fish ladder picture, and this one popped up. But again, we're trying to see, do we have conditions that will allow fish to swim up and successfully pass this dam through the fish ladder?
I will say, Chris, that if there was an award for picking out the worst quality pictures ever to be presented on the podcast, you would win the grand prize.
I'm a little technically challenged here. Yeah.
In terms of the model selection here, very, very unique fish ladder. I don't think there's any realistic way that you could get results that would be reasonable with anything other than a 3D model for this. It's also a pretty small structure, it looks like, and so probably not too computationally challenging to construct a 3D model of this area. Maybe if you, it's funny, sometimes you look at things and you look at them on the scale that we're used to seeing. So this doesn't look that large. If you pretended that this was a river system with a lot of bends in it, you actually might be able to get some reasonable results using a 2D model and just a lot of really, really, really small cells. But my first answer would be a 3D model. What would you say?
Yeah, I tend to agree with you. I mean, this is one where you could probably build a 1D model here if you really tried. I mean, you approximate the direction of flow. But again, your 1D model is not going to implicitly pick up the ineffective flow areas. So who knows what's ineffective in this?
Mm-hmm.
So my preference at a minimum would be to do a 2D model, but like you said, you would need some really small cells in here. But you can imagine that there's a lot of vertical stuff going on in here, especially at these drops. But even inside the pool, you probably have some upwells and things like that. You're not going to capture with a 2D model. So this is a short enough structure that if you do have that capability in the house to do 3D, that would probably be the right choice.
Very good.
Good. All right, that's it, Ben. You did great. A+. Nice work.
Awesome. Well, that was fun, Chris. It's always good to kind of, I think, go through these sort of comparisons. I also appreciate the fact that you shared that document from HEC. I think, again, that's going to be a really good one for everybody after they're done listening to this to go read through that. It's even more technical than the discussions that we had today. And obviously catered a little bit towards HEC-RAS specifically, particularly with the 1D and 2D and steady and unsteady. So great document. Definitely would encourage folks to review that. And again, also, if you have additional questions about 3D modeling, particularly Flow 3D, Brian Fox is somebody that we touch base with quite often on that kind of thing. So.
Yeah, very good. So let's wrap up. But reminder to everybody that we've got the upcoming class in Denver, August 1st, 2nd, and 3rd, and we're going to do the Pub and Grub at the same time on or the same week on the 2nd, which is Wednesday evening. And so keep your eye out for more information on that coming real soon. And if it interests you, we hope to see you there. What about the tournament, Ben?
Yeah, and obviously one more thing on the class and Pub and Grub. If you're an engineer or an engineering firm in the Denver area that are interested in sponsoring the event, we had some great sponsors at the Boise Pub and Grub that really allowed us to maximize that experience for everybody. So feel free to reach out to Chris or I if you're interested in helping out with the event. If you're interested in getting some more information, we're happy to provide that with you. And again, looking forward to seeing everybody in Denver this August. And then again, if you're interested, we are going to be hosting a RAS Madness Challenge, which is going to be a bracket challenge for everybody who wants to fill out a bracket and submit it. It's going to be through CBS Sports. The link for that sign up is going to be in the description of this video. So go ahead and click on that. Again, it's free to enter, and it's a fun event. The grand prize winner will have the opportunity to pick a registration for one of our 1D, 2D classes, either the in-person class in Denver or one of our online classes over the next year and a half. Anything else, Chris, before we head out for today?
That's it, Ben. It's as always great chatting with you and great doing this podcast, and hope to see as many of you out there as possible in the class and the Pub and Grub coming up in Denver. And yeah, we'll have a lot of fun with this RAS Madness thing too.
Awesome. Well, I'll get a last minute go Zags before the tournament starts here.
Go Zags. Let's do it.
Thanks again, everybody, for listening in today. This has been Full Momentum and HEC-RAS podcast. Until next time.